The definite integral of a function over an interval is defined as the limit of Riemann sums. From this definition, it follows that integrals enjoy certain properties. In this set of solved problems, I consider 4 problems that are directly related to and solvable by this definition of integrals as limits of Riemann sums. We start by reviewing the definitions. A Riemann sum of a function f over an interval from a to b is obtained by decomposing that interval into subintervals and by choosing a tag point tk from each subinterval. Let delta of xk denote the length of the kth subinterval. The point tk lies in that subinterval. The entries in the Riemann sum are of the form f at tk times delta of xk, and if the value of the function f at the tag point tk is positive, then this entry is the area of a rectangle placed on that interval and having the height f at tk. These are the blue rectangles shown in the figure below. If the function takes a negative value, then the entry f at tk times delta of xk is negative of the area of the corresponding rectangle. These are the red rectangles in this figure below. This summation k from 1 to n f at tk delta of xk of course depends on the choice of the decomposition of the interval into subintervals and on the choice of the tag points. Then one makes this more precise by letting these decompositions to get finer. And as one chooses various decompositions and tag points so that the length of the longest subinterval approaches 0, then at the limit one gets the definite integral from a to b f of x dx. And if f is continuous on the interval from a to b, then this definition does not depend on the various choices that one made. In particular, this integral from a to b f of x dx for a function which is continuous on the closed interval from a to b is independent of these choices of the tag points and of these choices of the decomposition of the interval from a to b into subintervals. And if the function f takes only non-negative values on an interval from a to b, then the definite integral from a to b f of x dx is the area of the domain bounded by the graph of this function on that interval. In the case of the figure on the right, the function takes also negative values. Therefore, the integral from a to b f of x dx is the difference of the combined area of the blue domains and the red domain. From this definition of integrals of functions over the interval from a to b as limits of Riemann sums, one obtains immediately the following properties of integrals. The first one says that the integral from a to a f of x dx is 0, and this is completely obvious because in this case the interval of integration has length 0. It is the interval from a to a, and this means that also every subinterval must have the length 0, and this means that all entries in all Riemann sums are 0, and therefore also their limit is 0. The second property is that the integral of a sum is sum of integrals, and this also follows from the fact that when one deals with Riemann sums, these are finite sums and they can be rearranged, and one always gets the same number regardless in which order one adds these entries in the Riemann sums. The third property is that the integral from a to b, a constant capital A times function f of x dx, is that constant times integral from a to b f of x dx. That is, a multiplicative constant can be taken outside of integration. In the Riemann sums, this multiplicative constant appears in every term and can therefore be taken outside of summation as a common factor. Fourth property says that integral from a to b f of x dx is negative of integral from b to a f of x dx. That is, if we exchange the roles of a and b, that is the endpoints of the intervals, then also the lengths of the subintervals get replaced by negatives of those lengths. Therefore we have property number 4. And property number 5, the additive property, tells us that the integral from a to b f of x dx is the integral from a to c plus the integral from c to b of the same function. This is immediate by the definition of the integral if c is between a and b. If c is not between a and b, then we may have to use the property 4 to get a justification for this property of definite integrals. The problems to be considered are the following. The first one, we know that the integral from 0 to 5 f of x dx equals 6 and that the integral from 0 to 3 equals negative 1. Our task is to compute the integral from 3 to 5 f of x dx. In the second problem, we have to compute the integral from 0 to 2 pi sine of x dx by using the properties of integrals and the definition of the integral as a limit of Riemann sums. In the third problem, we have to compute integral from negative 1 to 1 sine of x e to the negative x squared dx, also using the properties of integrals. And in the fourth problem, we are told that integral from 0 to 2 pi f of x dx equals 1, and our task is to compute the integral from 0 to 2 pi 2 times f of x plus sine of x dx. In this problem, we know that the integral from 0 to 5 f of x dx equals 6, and the integral from 0 to 3 f of x dx equals negative 1. Our task is to compute the integral from 0 to 5 f of x dx. To this end, we use the formula integral from a to b f of x dx equals integral from a to c plus integral from c to b of the same function. Therefore, integral from 0 to 5 f of x dx equals integral from 0 to 3 plus integral from 0 to 5 of the same function. We know what the integral from 0 to 5 is, and we also know the integral from 0 to 3. We plug those values in that were given to us in the problem. We get the equation 6 equals negative 1 plus integral from 3 to 5 f of x dx, of which we solve the integral from 3 to 5, and we get that the value of that integral is 7. Our task is to compute the integral from 0 to 2 pi sine of x dx using the properties of integrals and the definition of the integral as limit of Riemann sums. We start by drawing the graph of the sine function. When x equals 0, pi or 2 pi, sine takes the value 0. Between 0 and pi, sine takes positive values, and between pi and 2 pi, sine takes negative values. By the properties of integrals, integral from 0 to 2 pi sine of x dx equals integral from 0 to pi sine of x dx plus integral from pi to 2 pi sine of x dx. Now next observe that the area under the graph of the sine function and over the x-axis interval from 0 to pi is the same as the area of the domain between the graph of the sine function and the x-axis interval from pi to 2 pi. This follows by symmetry. So these blue and red domains have the same area. Therefore, the integral from 0 to 2 pi sine of x dx is the area of the blue domain minus the area of the red domain. And these areas are the same, therefore the integral is 0. In this problem, our task is to compute the integral from negative 1 to 1 sine of x e to the negative x squared dx by using the properties of the integrals only. And the solution is the following. We first consider the function that we have to integrate, that is the function sine of x times e to the negative x squared. We call it f. The graph of this function is shown here, and we observe that this function is odd function in the sense that the value of the function f at negative of x is negative of its value at x. This follows since sine has that property. Sine at negative of x is negative of sine at x. The function e to the negative x squared takes the same value at the points x and negative of x. So we have this symmetry, f at negative of x equals negative of f at x. And this means that the red domain indicated in this picture, that is the domain between the graph of this function sine of x e to the negative x squared and the x-axis interval from negative 1 to 0, has the same area as the domain between the graph of the function and the x-axis interval from 0 to 1. So we conclude that the red area equals the blue area. And then we simply observe that integral from negative 1 to 1 sine of x e to the negative x squared dx equals integral from negative 1 to 0 plus the integral from 0 to 1. And this means that this integral from negative 1 to 1 sine of x e to the negative x squared dx, which is now the blue area minus the red area. And since the blue area and the red area are the same, this means that this is 0. So we conclude that the integral from negative 1 to 1 sine of x e to the negative x squared dx is 0 without actually having to compute the integral in any particular way. We just use the properties of the function to be integrated, namely the fact that the function at x takes the value negative of f at x. In this problem, we know that the integral from 0 to 2 pi f of x dx equals 1. Our task is to compute the value of the integral from 0 to 2 pi of 2 times f of x plus sine of x dx. And we do that by using the properties of the integrals. We first observe that the integral from 0 to 2 pi of 2 times f of x plus sine of x dx equals 2 times integral from 0 to 2 pi f of x dx plus integral from 0 to 2 pi sine of x dx. This is by the properties of the integrals. And the integral from 0 to 2 pi f of x dx is known to be 1. Therefore, we may substitute 1 in the place of that integral, and we get that the integral for which we have to compute the value, that is the integral from 0 to 2 pi of 2 times f of x plus sine of x dx, equals now 2 plus integral from 0 to 2 pi sine of x dx. And we have to deal with this integral from 0 to 2 pi sine of x dx, and we observe that this integral is the difference of the blue area and the red area in this figure, which shows the graph of the sine function. And by symmetry, these areas are the same, therefore that integral from 0 to 2 pi sine of x dx is 0. We have already discussed this in a different problem earlier. We conclude that the integral from 0 to 2 pi 2 times f of x sine of x dx equals 2 plus integral from 0 to 2 pi sine of x dx, and this equals 2. So the answer is that the integral from 0 to 2 pi 2 times f of x plus sine of x dx equals 2.